Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thank you, as always, to our Patreon subscribers. We always really appreciate your support.
Nicole, what do you get when you subscribe to our Patreon?
You get bonus episodes. As we have mentioned many times, we have a long list of failures. Some of them are more complicated and complex than others. And so we take the simpler failures and we make our bonus episodes out of them, our exclusive content that is only available on our Patreon. Because our regular episodes come out every other Sunday, the Patreon episodes come out on the opposite Sunday. So if you subscribe to our Patreon, you get access to an episode every single week. And we also have enabled the special RSS feed so that you can listen to those bonus episodes in your regular podcast app. So we're not asking you to go to your regular podcast app and then over to Patreon for the bonus episodes and have to flip back and forth, because honestly, that would be really annoying and I probably wouldn't do that. So we've got a special RSS feed that gets you all of the content in one spot, which I think is really handy.
And if you heard that and thought, man, that is really neat, but I surely can't afford it, it costs less than the cost of avocado toast. That's not even a large thing of toast, not a large avocado, less than $5 a month.
$5 Canadian, which is like, what, $3 American, $4 American? Same with the euro. I think the US dollar and the euro are pretty similar right now.
They're pretty much on par right now when we're recording this episode. Also, interestingly enough, everything seems to have gone up in the last year, 6 months with inflation. Price to listen to mini episodes of Failurology remained the same.
Okay, question. Do you think avocado toast is so expensive because they have to account for the fact that at least 50% of the avocados aren't going to be used because they are good for an hour and then they're bad? They're not ripe, can't eat them. Then all of a sudden they're good and then they turn brown. Do you think that's why they're so high? Because, I mean, avocados are expensive relative to other fruit, but they're not that expensive. They're usually around $1 in Canada. But avocado toast is like $12 or $14, which is a lot of dollars.
I think there's a really big markup because back in the day, since I'm old, when I was growing up, avocado toast wasn't a thing. I really like avocado toast. It's delicious. I try not to order it when I go out because it's also like $16. I don't know why it's so expensive.
It's literally mashed avocado on toasted bread. I like it a lot as well, but I make it at home.
When I was living overseas, we had a number of avocado trees at the house I was staying at, and then also avocado trees that were in the neighbor's property that also just dropped avocados onto our property. So I could basically eat avocado toast for like the cost of bread, which is like 10 cents.
Okay, shall we move on to the news?
We shall, since that was kind of a long tangent of distraction there. This week in engineering news, eye imaging technology to help robots in cars see a little bit better. This technology was developed by all the brilliant people at Duke University while they weren't playing basketball. Engineers at Duke University and around the world, they're using LiDAR to improve the vision, if you could really call it that, of autonomous systems that are on trains and in cars, or just robotics in general. And what they use is a technology called LiDAR, which stands for light detection and ranging, which is basically a laser. It shoots out millions of pulses a second. The laser bounces off of stuff, and then they measure the time it takes for all those pulses, or for each pulse to come back. And from that, you can build a picture, a point cloud of what is in front of the laser, in front of the vehicle. And out of that, you can make various interpretations for things like road signs or trees or people or bicycles. And then you can train your machine learning system to react in various ways to all of these obstacles that are in front of the vehicle or the train or whatever the laser has been attached to.
So, Brian, do you work with LiDAR a lot?
I do work with a considerable amount of LiDAR data. The company I work for collects a lot of LiDAR data from aircraft. We've also collected LiDAR data from moving vehicles and other moving objects.
What would you say is comparable to LiDAR? It sounds almost like echolocation that a dolphin would use or a bat would use, except that it's with lasers.
Actually, that's a pretty good way to describe it. So yeah, with the echolocation, obviously that's a sound wave based thing. With lidar, it's light based or laser based. So there's just millions of laser pulses that shoot out every second, and they just bounce off things and return back to the sensor. There are a few disadvantages to lidar in general. If there's precipitation, so rain or snow, sometimes the laser will bounce off that, and you don't get very accurate returns. Ambient sunlight gets a little tricky as well. And then overall, just the size of the project area, depending on the point density that you're looking to achieve, sometimes it can just take a long time to collect all of this data
Right, because it's sending out millions of pulses.
per second, which is still fairly, it's fairly efficient. But if you're collecting a very large area, like 4,000, 5,000 square kilometers, it's just going to take time to collect all of the data for that area at 10 or 20 or higher points per square meter.
No, that's fair. Okay, I just thought of something. Because they use this laser detecting system, LiDAR. Okay, so if I'm in an autonomous vehicle and it's driving itself and it's dark outside, the car doesn't need lights, does it?
That would be correct. I mean, it probably should still have lights just for other drivers and visualization. But LiDAR doesn't need sunlight to operate. We've done a number of projects where we've actually flown them at night due to air traffic control concerns or just other concerns that we had for during the day. And the data on the office side was completely usable. The photo that we typically co-collect with the LiDAR data, that was obviously very dark, very black. So the photo component wasn't very usable from our camera systems. But the LiDAR that we collected at night was no different than the LiDAR that we collected during the day. So from a systems point of view, this LiDAR system wouldn't need to have lights, or the car wouldn't need to have lights for the LiDAR system to operate in the same way.
That would be a real trip to ride in, pun intended. I don't know if I would like that at all. I think that would be really freaky. I'm sure they would put lights on it, like you said before, for other cars and just, even the electric cars that we're seeing today still look like regular cars. I don't think we're quite ready yet for a different type of traveling machine.
Yeah, that would be a little different, probably a little off-putting too, if there were no lights on the car and your car was making all of these decisions based off interpretations from the sensor, especially if it was like a curving road and there was very little light. If there are no headlights on the car, just to navigate through curves or to stop at intersections, that would probably be a little unnerving.
Yes, for sure.
So another cool thing that researchers have been working on in the LiDAR field is something that's known as frequency modulated continuous wave, or FMCW LiDAR. This works very similar to optical coherence tomography, or OCT. This technology has been developed mostly for biomedical engineering fields since the early 1990s. They just needed to trade in high resolution for distance and speed, which is hopefully where FMCW LiDAR applications come into play. When I was going to university, there was a biomedical engineering program that was a minor, I believe, as part of the geomatics program. I didn't take it. A number of my colleagues did. Some of them have gone on to be medical doctors now, or they've significantly used their geomatics and their LiDAR background and kind of pivoted over to the medical device biomedical side of things. So I think it's really cool. I just didn't have the time or the inclination to also add on a biomedical component to my degree. So how FMCW LiDAR works, it sends out a laser beam that shifts between different frequencies and measures how long it takes to detect each of the frequencies that it sent out. So not only can this be used in any light source, but it also measures unimpeded beams. So they're sending out laser pulses on different frequencies. Different frequencies travel differently through different mediums. So this would allow them to map different body parts and different body structures in a different way than if they were just using a single frequency beam. One of the differences between FMCW LiDAR and kind of traditional LiDAR that we would use in the airplanes or would use in kind of a road-based vehicle, kind of the current LiDAR that we have right now, it works on a mechanical mirror setup. So there's a spinning mirror, and the laser hits the mirror, and as the mirror spins around it spins around at a fairly high rate of speed. That's kind of what allows the laser pulses to spread out across the project area to basically map the project area that you're looking to map, or at least the corridor width that you're looking to achieve. Where FMCW, it uses diffraction grating that works like a prism to spread the frequencies out as they travel away from the source. So slightly different technology in how the laser goes from the unit to the project area. So hopefully this will help the advancement of various other LiDAR systems.
If you want to read more about the research study helping cars see better, check out the link on the webpage for this episode at failurology.ca. Tired of washing dishes?
Dishwasher broken?
Flip the dishes over. There's a second side to those.
At least the plates.
We can't help you out with the bowls, but if it's the morning and you have no bowls, you're already in a bad spot if you wanted cereal.
Use a mug or something. You're probably still half asleep anyway. Who's going to judge you for eating cereal out of a mug?
We got your back. Flip the dishes. Now on to this week's engineering failure, the Chalk River nuclear accident. So this one is interesting. I talked recently at a conference, which, if I'm being honest, we're recording this before I've gone to the conference. So the conference is a future thing for me right now. But when you listen to this, I'll already have been there. But my session talks about different types of failures and breaking them up between unknowns, things we don't know yet, new territory, versus mistakes that are made but not on purpose, accidents happen, versus things that we know are wrong and we do them anyways. And so I feel like this Chalk River nuclear accident, or both of them, we're going to talk about two, falls under that first category. This is uncharted territory at the time. These accidents we're going to talk about two accidents. They both happened in the 1950s, and it was very, very early days for nuclear technology and nuclear reactors as far as power generation. And so I think these are really interesting and should definitely be taken with a grain of salt. We know a lot more about nuclear now than we did back then. We're going to get into the failures for Chalk River, but I will say, and I will probably repeat throughout the episode, that it doesn't seem like the 3 Mile Island or Chernobyl reactor operators or manufacturers, designers really took lessons from Chalk River, because we're seeing kind of patterns, mistakes that were made, and not necessarily that they're making the same mistake, but that the system allowed the mistake to go unnoticed. The processes in place didn't require a certain level of training on this equipment, and those things are what led to the failure. So I do think it's interesting that we're not quite learning the lessons that we should be. Not surprising though, if I'm being honest, but let's get into it and we'll talk about it. So the Chalk River Laboratory site is located along the Ottawa River, 180 kilometers northwest of Ottawa, just on the Ontario side of the Ontario-Quebec border and east of a town called Chalk River.
For anyone that doesn't know, Ottawa is the capital of Canada. It's not Toronto. It's Ottawa, Ontario.
That's true. Ottawa is the capital city of Canada, and Toronto is the capital city of the province of Ontario. The Chalk River facility opened in 1944 on a 36 square kilometer campus, and when it first opened, it was referred to as Petawawa Works. Say that 3 times fast. The site specialized in major research, development, and advancement of nuclear technology, particularly the CANDU reactor technology, and the people on the site had expertise in physics, metallurgy, chemistry, biology, and engineering. There have been 2 Nobel laureates who have worked at the Chalk River Labs. Bertram Brockhaus received the 1994 Nobel Prize in Physics for his work on the neutron spectroscopy while at Chalk River from 1950 to 1962. And Sir John Cockcroft shared the 1951 Nobel Prize in Physics with Ernest Walton for splitting the atomic nucleus. He was also instrumental in the development of nuclear power and served as director of the Montreal Laboratory in 1944 and the creation of the Chalk River Labs itself. The lab is still open today, but they don't generate nuclear power. Today, it's owned by Canadian Nuclear Laboratories, which is a subsidiary of Atomic Energy of Canada Limited, operating under contract by the Canadian National Energy Alliance, a private sector group led by SNC-Lavalin. So there's a number of umbrellas there. But essentially they make nuclear, it sounds like they make isotopes for medical purposes. So the laboratory is still there. They're not doing any power generation. They're not doing any reactor testing. They're mostly working within the medical field, providing various isotope products for the medical field.
The Chalk River site housed the first nuclear reactor outside of the USA called ZEEP, which stood for Zero Energy Experimental Pile. I think it's a great acronym. I hope I'm saying it right for ZEEP. I'm not sure if it was supposed to be ZEEP since this was in Canada. Either way, I think it's a great acronym, especially for the playoff on Canada, US, different pronunciations of the last letter of the alphabet. ZEEP, which is what we're going to call it in this episode, was one of the world's first heavy water reactors and was designed to use natural or unenriched uranium. Its development led to the creation of the NRX and NRU reactors as well as the CANDU nuclear reactors. ZEEP was decommissioned though in 1973. Interestingly, at one time, Chalk River produced a third, that's 33.33% repeating, of the world's medical isotopes and about half of North America. So they produced a considerable amount of isotopes for medical purposes. Despite their claim to peaceful use, though, the Chalk River facility sold 254 kilograms of spent reactor fuel in the form of plutonium to the US from 1955 to 1985 for the production of nuclear weapons. So they're doing some pretty good things on the medical isotope front, some probably not so great things on the selling plutonium side. There have been at least 10 reactors in operation at Chalk River through the time period of 1945 to 2018. All the reactors that were there, they were all different styles and different capacities. Like Nicole mentioned, we're going to talk about 2 of these today, both of which suffered accidents in the 1950s.
The first one happened in 1952 with the NRX reactor, or National Research Experimental, which was an 8-meter diameter by 3-meter tall, heavy water moderated and light water cooled nuclear reactor that generated 30 megawatts of power. Because I know you're wondering, heavy water is water that instead of having 2 hydrogen elements, the hydrogen is replaced with 2 deuterium atoms. Instead of a chemical formula of H2O, heavy water is D2O. And the heavy water slows down the neutrons better than light water, so they react with the fuel, which in this case was uranium. Light water is essentially drinking water, equivalent, give or take, to the water that comes out of the tap. Although, of course, you wouldn't drink light water that's being used in a nuclear reactor because it's full of radiation. Now, the NRX reactor is different from Chernobyl and 3 Mile Island, both of which we've covered on previous episodes, so please go check those out. But they all work the same conceptually. The reactors use heat generated from a nuclear reaction to create steam. The steam turns a turbine, and that generates power. A moderator, which in this case is heavy water, controls the reaction rate. Control rods are also used to control the reaction. Inserting the control rods or removing the moderator will slow down the reaction. The moderator does this by slowing down the neutrons, causing a chain reaction that's less likely with fast-moving neutrons. So as I mentioned, these are different from Chernobyl and 3 Mile Island. The Chernobyl reactor used graphite as the moderator, and 3 Mile Island reactors used light water as the moderator. As we mentioned, this one used heavy water, so it was more like 3 Mile Island, but with a better moderator. So heavy water is a better choice for moderating the reactor because it's more effective.
On to the first failure that we're going to talk about. On December 12th, 1952, the NRX reactor suffered a partial meltdown due to operator error and mechanical problems in the shutoff systems of the reactor. During a test, some of the tubes were disconnected from the high-pressure water cooling system and connected to a temporary cooling system by hoses. One of the tubes was cooled by airflow. During the test on low power, with low coolant throughout the core, the reactor supervisor noticed several control rods being pulled from the core, which would increase the reaction speed. The supervisor went to the basement to check and found an operator opening pneumatic valves. After putting the valves back into the correct position, some of the control rods didn't re-enter the core. The power level exponentially increased, doubling every 2 seconds, and tripped the reactor. So there were a couple of emergency backups, a couple of emergency rods. There were in fact 4 emergency control rods, but due to mechanical defects, 3 were not inserted into the core, and the 4th took 90 seconds to insert, which in nuclear meltdown, nuclear reactor time, I feel is an eternity.
Definitely. I can't remember the exact timing, but I think Chernobyl and 3 Mile Island, it was definitely within minutes that the reactors ran away. So, I mean, 90 seconds for an emergency system in this application is, in my opinion, unacceptable. Not to mention 3 of the rods weren't inserted at all. So, not good.
Speaking of timing, after about 10 seconds, which is probably about the time that it took me to say that sentence, the power levels reached 17 megawatts, which was a little over half of the intended output of the reactor. 10 seconds, half the intended output of the reactor. That's increasing power incredibly quickly. So the cooling water does what water does, it boils off, and some of the temporary tubes ruptured and the power continued to rise. Not off to a good start here. The moderator, the water, is starting to boil off. The temporary tubes that were there, they decided not to work anymore. Power level continuing to rise. Not over 9,000 yet, but it's continuing to rise. 14 seconds later, the heavy water was drained from the reactor. So we are 24 seconds into this adventure.
And the 4th control rod, the only one that's working, is maybe a third of the way inserted.
This is not a good situation. So power peaks at 80 megawatts, which is almost 3 times the intended capacity, then decreases as the heavy water was drained and was back down to 0 megawatts 25 seconds later. So this is a very fast spike and then a very fast drop off. Some of the fuel elements melted, and the reactor cylinder, called a calandria, was pierced in several places. The cooling system kept running to remove decay heat, but leaked 4,000 cubic meters of contaminated coolant water into the basement of the reactor building over the next few days. So for something that takes not very much time, less than a minute, there's some fairly catastrophic consequences that have happened as a result of this.
Just for a little bit of context here, this reactor, its nameplate capacity, which I realize it did exceed that, but its intended capacity is 30 megawatts. For comparison, Chernobyl had 1 800 megawatt reactor and 3 1,000 megawatt reactors. So this is a relatively small nuclear reactor, and I also don't believe it's providing power to a grid. The reactors at Chalk River may provide power to the site itself for some of the process work that they're doing there. I don't think they're providing power to the public, which I think is a good thing in this case. Not that it's okay that this accident happened, but the lack of impact on neighboring sites' power, as well as the small size of the reactor, I think made this a much better outcome than it could have been. So the cleanup for the NRX reactor took several months, and they had help from the US Navy, including future US President Jimmy Carter.
Interestingly enough, on the topic of presidents, because I seem to know a lot of random things, U.S. presidents, while they're in office and also while they're out of office, aren't allowed to drive on public roads. So, from what I remember, they're still allowed to drive on private residences. A number of presidents have, giant farms that they kind of drive around in, but when you are a U.S. president, I think for good reason, you have the Secret Service and chauffeurs and highly trained people for that are trained in egress driving and escape sort of driving scenarios. They drive you around absolutely everywhere, and that continues after your term in office is done. Whether it's a single term or whether it's 2 terms. One of the I guess the downfalls of being the U.S. president is that you can't drive anywhere, which if in your previous life you were really into cars, you just like driving vehicles around, you got to be driven around all the time, and that doesn't seem like it would be a ton of fun.
I think that sounds fun as someone who can drive, but when I'm told I can't drive, I'm not sure if being chauffeured would feel quite the same. I think I would like driving. But yeah, like you said, most of them have farms. I think, wasn't Jimmy Carter a peanut farmer?
He was a peanut farmer because when he became president, he placed his peanut farm, even though it was kind of a fairly mediocre business, He placed that into trust so there wasn't any sort of conflict of interest. I believe both the Bushes, H.W. Bush and George W. Bush, they both have ranches in Texas, and I believe they are allowed to drive on their ranches since it's private land under the supervision of the Secret Service. I'm not 100% on that one, but I do know that it's very much frowned upon for presidents to be driving.
So chauffeuring is one thing, but it sounds like you're never really left alone. And I think that would grow old real fast as an introvert. But back to Chalk River. As part of the cleanup effort, they removed and buried the reactor core and the calandria and replaced both of them. The refurbished reactor was back up and running in 2 years, and it ran until 1992. So they were able to rebuild this reactor, get it back on board, and it ran for more than 30 years after the accident, which I think also says something to the scale and size of the accident here, because again, like we saw in Chernobyl and 3 Mile Island, those reactors weren't rebuilt, didn't come back online. There were other reactors on the site that continued to operate, but the ones that had the meltdown, and I understand those were more catastrophic and they were larger reactors, much more devastating outcomes, but I do think it says something here that this one was able to be rebuilt and went back into operation. The investigation found that even though there were operating errors with the NRX reactor, they were not outside of the normal range of human error, and that the design and management was intended to be safe even with human error. However, there was a combination of mechanical issues along with the human error, which led to the failure, suggesting that some improvement is necessary. And this is what I was talking about before when I said that it seems like we didn't quite learn our lesson, because human error has played a factor, I think, in all nuclear accidents to date. And it will continue doing so until we build systems that protect against that. And I realize you can't avoid it entirely, but I think more safeguards can be put in place to protect from human error and prevent more of these meltdowns from happening. The Atomic Energy of Canada Limited report called for a better system of review and inspection to be established to relate the design considerations to current practice. So far in 1952, this was pretty early days as far as nuclear reactors go and what we know about how they worked. As I mentioned, it's the same problem as Chernobyl and 3 Mile Island, different cause, but same problems with a runaway reactor that they couldn't get under control. As I said, due to the small size of the NRX, the damage was minimal, and fortunately, they were able to rebuild it.
So we said we were going to talk about 2 Chalk River nuclear incidents. So we've talked about the first one, more or less, I think. The second one occurs in 1958, so 6 years after the NRX incident occurs. In 1958, the NRU accident occurs. So the NRU accident, which stands for National Research Universal Reactor, occurred on Saturday, May 24th, 1958. So the NRU reactor went live on November 3rd, 1957, a decade after the NRX, and was initially designed as a 200 megawatt reactor fueled with natural uranium.
I do think it's interesting that the NRU accident, that one that we're talking about now, happened about 6 months after the reactor went online. Because that's also something that's common, which tells me that we're not providing adequate training for reactor operators. Because if it's failing so quickly, brand new equipment, in theory, none of the safeguards have been damaged. Everything should be, it should just be general maintenance at that point. So the fact that these accidents are already happening tells me that more can be done on the training side so that operators understand the equipment and what they're doing. And to be fair to them, I'm not a nuclear physicist. I'm not a reactor engineer. This is well outside my expertise. I don't feel as though I have the expertise to operate a reactor. I think this is a very highly skilled position that it's not something you can just jump into. And so I understand that there's a lot of moving parts. There's a lot of things going on. There's a lot to understand and wrap your head around. I just think that it is critical that we get the right people and adequate training for these reactors all around the world, especially with all of the things going on in the world today. We're seeing nuclear come more to the forefront of the energy discussion. For a while, it seemed like we were not anti-nuclear, but there's still some fear. Chernobyl really scared some people, and I don't blame them. And so there's a lot of hesitation around nuclear, but we're starting to see that turn a corner. And I think nuclear is going to become much more common going forward. And so then these lessons learned are just that much more critical.
So the NRU reactor was initially designed as a 200 megawatt reactor, like I'd mentioned, fueled with natural uranium. It was later converted, though, to a 60 megawatt reactor in 1964 with high enriched uranium, and to a 135 megawatt reactor in 1991 with low enriched uranium. So it's gone through a couple different cycles, different power outputs, different configurations, different reactor material, but it has a fairly long life, I guess, even after this incident that occurs, in 1958. In 1958, several metallic uranium fuel rods overheated and ruptured in the reactor core. One rod caught fire and was torn in two. It was being removed from the core with a robotic crane at the time, and the large half of the rod fell into the containment vessel, still on fire. So it's a situation that goes from not very good to bad to worse to like really, really bad. The scientists and the maintenance personnel were able to extinguish the fire with wet sand, which is probably not the first thing I would think of to use to put out a fire on a nuclear rod, but apparently it worked. It was extinguished. Kind of makes sense. It's wet, it's damp, it will just cover the rod. So yeah, I can, after much thought, I can see how this would be a good tool to use for firefighting.
I think I went through the same thought process when I read wet sand. I immediately thought, that's interesting. And then, yeah, the more I thought about it, the more I was like, okay, I guess that tracks. That makes sense. But yeah, I wouldn't have called that out without someone telling me first. By the time the fire was extinguished, a significant amount of radioactive combustible products had contaminated the interior of the reactor building and the adjacent laboratory site. Unfortunately, at the time, the ventilation valves were in the open position, which also contaminated some of the area outside of the building as well. I'm going to be honest, I went through a number of reports. Oddly enough, there was a lot more data on the initial NRX failure that happened in 1952 than there was on the 1958 NRU accident. For the earlier one, I was able to find the full investigation with all of their findings, their recommendations, conclusion. But for the second one, I did a lot of Googling and I wasn't able to come across that report. I did find a lot of data about whether or not people were injured from the accident and the long-term health effects of the accident, which I thought was interesting. It seemed like the health impacts of the accident kind of overtook the discussion surrounding it in general. And so, yeah, I wasn't able to figure out why the rods overheated and caught fire. If any of you listening know why that happened or have any more data on this, please reach out to us. We'd love to chat with you and maybe do a follow-up episode. The cleanup took 3 months and the reactor was operating again by August. So this one was only down for 3 or 4 months while they did the cleanup, which is also good news and again speaks to the size of the reactor and how bad the accident was. Staff involved in the cleanup took efforts to mitigate exposure and were monitored over the following decades. For the most part, the message has been that there are no significant health impacts from this accident. That said, I did find mention that one corporal involved developed unusual skin cancers and eventually received a disability pension.
So there you have it, the Chalk River nuclear reactor accidents. 2 nuclear incidents in the 1950s when nuclear engineering was in its infancy. Luckily, both accidents were not catastrophic and the reactors came back online after the cleanup. The NRX and NRU accidents taught us a ton about reactor safety and operations, although apparently not enough because 3 Mile Island followed in 1979 and Chernobyl more recently in 1986.
For photos, sources, and an episode summary from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find us. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us on our Patreon page. And remember, Patreon is $5 Canadian a month for twice the episodes, twice the fun, way more train tangents. Check out the show notes for links to all of these, and thank you everyone for listening. Tune into our next episode where we'll talk about FedEx Express Flight 80. Yes, another plane one, Brian's favorite. What seemed like a windy landing was actually exasperated by the plane's unstable design. Bye everyone. Talk soon.